Hey everyone, and welcome to this video on sorting algorithms. Today we take a deep dive into how computers arrange data efficiently. Sorting might seem simple, but behind the scenes it's one of the most important operations in computer science. So we'll cover some of the most well-known sorting algorithms, including SelectionSort, InsertionSort, Bubbl Sort, MergeSort and QuickSort, and we'll also see how they compare. Sorting is a fundamental problem in computing, because in many real-world applications a significant portion of runtime is spent on sorting operations. It's not just about ordering values. Sorting is a prerequisite for tasks like binary search, efficient data processing, or organizing results in a distributed system. So understanding sorting helps you write faster programs and make smarter choices when dealing with large data. Sorting algorithms are generally split into two categories. We have the internal sorting, where all data fits into memory, like when working with arrays or linked lists, and we have external sorting, where the data is stored on slower external media like hard drives. External sorting is important when dealing with large datasets such as those in big data or databases. Also, some sorting algorithms are called stable. A stable sort preserves the relative order of elements that are equal. So imagine you have a list of people sorted by their name in alphabetical order, and now you want to sort them by name. If two people have the same age, a stable sort will keep them in the same name order they had before. This property is important when sorting by multiple criteria. The first algorithm we want to look at is SelectionSort. SelectionSort works by repeatedly selecting the largest or smallest element and placing it at the beginning or at the end of the list. So it's like finding the largest or smallest card from a deck and moving it to the beginning or the end. And we do this again and again. In the code we basically loop through the list, find the largest item and swap it into place. So now let's look at an example on how a selection sort exactly works. We have these items given and we want to sort them in ascending order. In this example, selection sort looks for the smallest element in the unsorted part and moves it to the front. So let's start the algorithm. So in the first pass, the algorithm iterated through the list and found the smallest element, which is 1 at the index 2. And then it sorted 1 with the first element, which was 8. So now 1 is on its correct position. So now we only have to consider the remaining unsorted portion, which is 3, 8, 6 and 2. We iterated over the list again and found our smallest element, which is 2 at the index 4. And then we sorted with 3 at the index 1. So 2 is now also in position and the sorted part grows to 2 elements. And we repeat this until our list is sorted. This algorithm is simple, but its performance is not great. It always does the same number of comparisons even if the list is nearly sorted, because we have to compare each element to every other element in the list, which leads us to a time complexity of big O of n squared, which is not very efficient. Another sorting algorithm is InsertionSort. InsertionSort mimics the way we sort cards in our hands. So we start with one item and insert the next one in its proper place and so on. So at each step the already sorted part grows, and the current element is placed in its correct spot by shifting other elements. So we start with just the first element 8, which we consider to be already sorted, and then we go through the rest of the list and insert each item into the correct position within the sorted part on the left. So we compare 3 with the sorted part, which is 8. Since 3 is smaller than 8, we shift 8 one position to the right and insert 3 at the beginning. Then we want to insert 1 into the sorted part, 3 and 8. 1 is smaller than 3 and 8, so we shift both to the right and place 1 at the beginning. It performs very well on nearly sorted data, so it has a linear time complexity in the best case, because if our data is already sorted we just have to iterate through our list once. But in the worst case, like a reversed list, its time complexity also becomes n squared. Then we have Bubbl Sort. Bubbl Sort is simple, large elements bubble up to the end by swapping with smaller neighbors. So we compare each pair of items and swap them if they're out of order, and we do this over and over until the list is sorted. The first thing we do is we compare 8 and 3. 8 is greater, so we swap them. Then we compare 8 and 1 and swap them, then 8 and 6, and then 8 and 2. The largest number 8 now moved all the way to the end. That position is now considered sorted. The next thing we do is we compare 3 and 1 and swap them. 3 is already smaller than 6, so we go on, and then we swap 6 and 2, so 6 is now before 8. Bubbl Sort is easy to understand but not very efficient. Even with optimizations, Bubbl Sort is generally too slow for large datasets, so we have a time complexity of n square. Still, Bubbl Sort is often used for educational purposes or small input sizes. Now we have a more powerful algorithm which is called MergeSort. MergeSort is a divide and conquer algorithm, which basically means that we divide our problem in smaller partial problems. It splits the list into halves, sorts each half recursively, and then merges them together in sorted order. So we split our list in half until each sublist contains just a single element, and then we can start merging them back together. We compare 4 to 9. 4 is smaller than 9, so we can insert 4 and then 9 into a new list. Then we merge the two lists 4, 9 and 7. So we compare 4 and 7. 4 is smaller, so we can insert 4. Then we compare 7 and 9. 7 is smaller, so we can insert 7 and then 9. Then we merge 1 and 5. 1 is smaller, so we can insert 1 and then 5. And then we can combine our two lists 4, 7, 9 and 1, 5. So we compare 1 and 4. Then we compare 4 and 5. Then we compare 5 and 7. And the rest of the list is already sorted, so we can insert it. Then we do the same thing for the list on the right. And in our final merge, we combine these two lists. MergeSort performs very well with time complexity of n log n, because in every iteration we divide our list in half and we do this n times. Also it's stable, so it preserves the order of equal elements. The trade-off we have is that it requires additional memory for merging. Still, MergeSort is often used in real-world applications, especially where consistent performance is critical. The last sorting algorithm we want to look at is QuickSort. QuickSort is one of the fastest sorting algorithms in practice. Like MergeSort, it uses the divide and conquer principle, but it partitions the list around the chosen pivot element, then it recursively sorts the two sides. There are different ways to choose the pivot element, for example the first or the last element, or we choose it randomly, which is called random QuickSort. So again, let's look at an example how QuickSort works. We choose the first element as the pivot element, so our pivot is 9. In the first iterations, all elements are smaller than 9. So we can swap it with the last element. So now all elements on the left of the pivot are now smaller than the pivot. 9 is now sorted and we choose our next pivot element, which is 6. Then we iterate through the list again and mark the first element, which is greater than 6. In this case it's 7. So now we move it until all smaller elements are on the left side. Two was the last element we swapped with 7, so we can swap it with the pivot 6. Again, all elements on the left of the pivot are now smaller and all elements on the right are greater. Now we have to repeat our algorithm recursively. So we sort the list on the left of the pivot and on the right side. We choose 2 as our pivot element and mark the first element that is greater than 2, which is 4. And again move it with smaller elements than the pivot element. 1 was the only smaller element, so we can swap 1 and 2. The list on the left side of 6 is now sorted, so now we only have to sort the list on the right side of 6. QuickSort is very efficient in the average case, about 1.38 times n log n, which leads to a time complexity of big O of n log n, but it can degrade to n squared in the worst case if the pivot element is poorly chosen. For example, if we always choose the smallest or the largest element, in this case in every iteration our list only shrinks by one element. It's also not stable, but it's in place, meaning it doesn't need extra memory. Let's now compare all the algorithms. SelectionSort is simple but slow and always does the same number of comparisons. It is unstable and has a time complexity of big O of n squared. InsertionSort is fast on almost sorted lists but slow on reversed ones. So we have a best case running time of n and a worst case running time of n squared. Then we have Bubbl Sort. It's good for educational purposes but not very practical for big lists. That is because it has a running time of big O of n squared. Bubbl Sort is also stable. MergeSort is fast and stable but needs extra memory. It has a time complexity of n log n. And then we have QuickSort. It's also fast and in place but not stable. We also have an average running time about n log n. Choosing the right algorithm depends on your data, its size, whether it's already sorted, and how much memory you can use. There are also other sorting methods worth knowing. For example, shell sort, which improves insertion sort by comparing distant elements. Then we have radix sort, which is a non-comparing sort. It's working digit by digit and it's very fast on integers. And then we have also heap sort, which uses a tree structure to maintain order. Each of these has unique use cases and also advantages. So that was a tour for the world of sorting algorithms. Sorting is more than just a technical detail, it's the foundation of efficient software. I hope this gave you a solid overview of how different algorithms work and when to use them. If you found this video helpful, give it a like and subscribe for more CS topics.